Let me tell you something I have never enjoyed admitting, something that even now, after all these years, makes me a little uncomfortable. The universe, in one very specific way, proved me wrong, not slightly wrong, not in a small and unimportant detail, fundamentally wrong about something I believed with everything I had for many years with complete confidence. I spent years arguing that two particles, separated by enormous distances, could not possibly influence each other instantly. I was so bothered by this idea that I gave it a name. I called it spooky action at a distance, and I was completely, utterly convinced it could not be real. I staked my reputation on this. I built arguments against it. I wrote papers against it. I told my colleagues firmly and clearly that this could not happen. But it does happen. The universe decided to surprise even me, and today I want to tell you the full story, not just what I believed, not just why I believed it so strongly, but how the universe answered me. Because even though I was wrong about this, the journey is one of the strangest and most beautiful adventures in all of science. And I think you deserve to hear it honestly. To understand this story, I first need to tell you something about the very small, about a world so tiny you will never see it with your own eyes, no matter how good your eyesight is. Everything around you, the chair you are sitting in, the air you are breathing, your own body is made of incredibly small pieces, atoms, and inside atoms, even tinier things, electrons, protons, neutrons. These are the building blocks, the smallest ingredients from which everything in the universe is constructed. For many decades, brilliant scientists worked very hard to understand how these tiny pieces behaved, and what they discovered was deeply, profoundly strange. At the scale of the very small, nature seemed to follow completely different rules than the ones we see in our everyday lives. A particle did not simply sit in one place. The way a ball sits on a table, before you measured it, it seemed to exist in many places at once. It did not simply have one definite property. The way a ball is either red or blue, before you looked at it, it seemed to have no definite property at all, as if the act of measuring, the act of looking, was what forced the particle to finally choose. Many scientists accepted this and built a theory around it. They called it quantum mechanics, and this theory worked extraordinarily well. It could predict the results of experiments with remarkable accuracy, but I could not fully accept it. Something about it troubled me very deeply. You see, I believed very strongly that reality existed whether we looked at it or not. A rock sitting on a mountaintop does not disappear simply because no one is watching it. It is still there. It is still real. It still has its size, its weight, its color. I believed this about everything in the universe, including the tiniest particles. I believed that quantum mechanics, however useful it was as a tool, could not be telling us the whole truth. Something I was certain was missing, and I was determined to find it. To explain what bothered me most, let me share with you a thought experiment. I worked on this with two colleagues, Boris Podolsky and Nathan Rosen. We published it together in 1935. We called it the EPR argument. Our goal was simple. We wanted to show as clearly and honestly as possible that quantum mechanics was incomplete. Here is the idea. Imagine you have a pair of gloves, one left, one right. You separate them without looking at either one. You place one glove in a box. You place the other glove in a second box. Now you give one box to a friend. You keep the other. Your friend sails across the ocean and takes their box far, far away from you. Many months pass. One day you open your box. You look inside. You find the left glove. At that exact moment, you know with complete certainty what is in your friend's box on the other side of the world, the right glove. You did not need to wait. You did not need to send a message. You knew instantly the moment you looked. But did anything travel between the two boxes? Of course not. The gloves were always left and right. They were decided the moment you separated them. You simply did not know which was which until you opened the box. Nothing mysterious happened. Nothing traveled across the ocean. The answer was already there, waiting from the very beginning. This is what scientists call a correlation. Two things that are connected, not because something reached between them, but because they were linked from the start. Now, in quantum mechanics, particles can be linked together in a special way. Scientists call this entanglement. Two particles can be created together in a way that connects them deeply. Then they can be sent apart, one here, one there, even two opposite sides of the world. And when you measure one of them, you instantly know the state of the other, no matter how far apart they are. This sounded to me exactly like the gloves. I believed the particles were like the gloves. I believed they already carried their properties inside them from the moment they were created together. We simply could not see those properties until we measured them. They were hidden, but they were real. They were always there, waiting. Just like the gloves, I called these hidden properties exactly that, hidden variables, and I was very confident that quantum mechanics was incomplete because it did not account for them. The reason this question mattered so much to me was connected to something I had discovered much earlier in my life, something from my own work. I had shown that nothing in the universe can travel faster than the speed of light, nothing at all, not objects, not energy, not information, not anything. The speed of light is the absolute maximum, the universal speed limit, and I was very confident in this. Now think about what would have to be true if the particles were not like the gloves, if they did not already carry hidden properties inside them, if a particle genuinely had no definite state until the moment it was measured, and yet measuring one entangled particle instantly determined the state of the other, far away, then something would have to pass between them, some kind of influence, some kind of connection, and it would have to pass instantly across any distance. Instantly means faster than light, and faster than light, according to my own theory, is impossible. This is why I use the word spooky. In a letter to my colleague Max Born, I wrote about this idea with real discomfort. The German word I used was spukhaft. It means ghostly, eerie, something that should not happen in a sensible, orderly universe. I believe deeply in what scientists call locality, the idea that something can only be affected by things that are near it. Nothing reaches across empty space and acts instantly on something far away. This belief felt so natural, so obviously true, that I could not imagine it being wrong. So I held firm. The particles must already carry their properties. Quantum mechanics must be incomplete. The universe must be local and orderly, even at its smallest scales. I waited patiently for the proof that would vindicate me. Now I must be fully honest with you, and I have always believed that honesty is the most important quality a scientist can have, even when the truth is uncomfortable. I was wrong. After my time, a brilliant physicist named John Bell made a discovery that made it possible to settle this question once and for all. Not through argument, not through philosophy, through a real experiment. Bell found a way to design a test that would give a different answer depending on who was right, me or quantum mechanics. If I was right, if the particles truly did carry hidden properties from the beginning, like the gloves, then when scientists measured many, many pairs of entangled particles, the pattern of results would have to stay within certain boundaries. Bell calculated exactly what those boundaries were. He called them Bell's inequalities. If hidden variables existed, the results would obey those boundaries always. But quantum mechanics predicted something different. It predicted the results would break those boundaries, go beyond them. So the question became very simple. Run the experiment, look at the results. Do they stay within Bell's boundaries or do they break them? Scientists performed this experiment, first in 1982 by a physicist named Alain Aspect in France, then again and again, many times, by many different scientists with greater and greater precision. Each time the results were checked carefully. Each time the answer was the same. The boundaries were broken every single time. Quantum mechanics was right. I was wrong. The particles do not carry hidden properties. They genuinely have no definite state until the moment of measurement, and when you measure one entangled particle, the other one, no matter how far away, instantly becomes defined. I want you to sit with that for a moment. Two particles created together, sent to opposite sides of the universe, and they remain connected, genuinely, truly connected, not like the gloves in the boxes, not because the answer was already there, waiting, but because until you look, there is no answer, and the moment you look at one, the other instantly has its answer too, across any distance, with no signal traveling between them. Now I suspect something is bothering you. If entangled particles really do influence each other instantly, does that not break my theory of relativity? Did I not say that nothing can travel faster than light? The answer is no, nothing is broken, and the reason is subtle but very important. When you measure one entangled particle, you cannot control what answer you get. The result is genuinely random. You might find it in one state or the other, and there is absolutely nothing you can do to choose which. So yes, your result is instantly connected to the result of the other particle, far away, but since you cannot control your own result, you cannot use this connection to send a message. You cannot encode information into it. You cannot communicate with someone on the other side of the world using entangled particles because you have no way to decide what signal to send. Think of it this way. You and a friend each receive one particle from an entangled pair. You are on opposite sides of the world. You each measure your particle, you each get a result. To you, your result looks completely random. To your friend, their result also looks completely random. Neither of you sees anything unusual. It is only later, when you meet and compare your results through perfectly normal conversation, that you discover something remarkable. Your results are always perfectly correlated. They match every single time in exactly the pattern quantum mechanics predicted. But by the time you compared, you used normal communication, you did not send information faster than light. The connection between the particles is real, but it cannot be used as a channel. It cannot carry a message. The universe is strange enough to be truly spooky, but clever enough to remain consistent with its own deeper rules. When I think about this story, about entanglement, about my argument, about being proven wrong, I do not feel embarrassment. I feel wonder. Wonder because it means the universe is even stranger, even richer, even more magnificent than I ever imagined. I spent my entire life trying to understand reality. I believed it was local. I believed it was orderly. I believed it was predictable at its deepest level, and in many ways it is, but in this one extraordinary way it is not. Two particles can remain connected across any distance in a way that has no equivalent in our everyday experience. There is nothing in our normal lives that prepares us for this. It is, by any measure, one of the strangest discoveries humans have ever made, and yet it is true, proven, tested, confirmed again and again. I think the greatest scientists are not the ones who are always right. They are the ones who are brave enough to ask difficult questions, honest enough to follow the evidence wherever it leads, and humble enough to accept the answer even when it surprises them. The universe does not belong to us. We do not get to decide how it works. We can only watch, we can only listen, we can only learn. And if it shows us something we did not expect, something strange, something spooky, something that makes us uncomfortable, the only right response is to open our eyes a little wider and pay a little closer attention. That is what I wish for you, not that you accept everything without question, but that you stay curious, that you keep asking, and that when the universe answers you in a way you never imagined, you do not look away, you lean in, because that is where the real understanding begins.